right? So assume there's an inclined surface like this. Let's say it has an angle of inclination. Okay, let's take a general case, theta. Assume it's a smooth surface. Okay. We still have not discussed how to write equations based on friction. So for now, we'll assume the surfaces are smooth. Now, if you place a block on this smooth surface, okay, not here, maybe somewhere here, and release it, what would happen?
It will slide down.
Yeah, if it's a smooth surface, it would slide down. Okay, no friction. Fine. So even if you release it from rest, it is not going to continue to be at rest. So on its own, it cannot be in equilibrium. But we can do one thing, we can support the block by tying it to a string. So let's say you are given a system like this. Now, if the block is in equilibrium, first, what are the forces acting on the block? Next, how much is the magnitude of each force? Okay. Its mass is given as m, angle of inclination is theta, and acceleration due to gravity, take it as g. So all answers will be in terms of m, g, and theta, not numbers. Okay. So think about this, all of you. The block is held stationary there. It's in equilibrium. So yeah, Saket, tell me, what all forces do you think act on this block?
So gravitational, normal, and tension.
Okay. See, any object that has mass and is close to Earth, you will definitely have to consider gravity. That is the weight of the object. Fine. And Saket, how did you say there will be a normal force acting on it? Or what made you think about normal force?
Sir, because the object, the M object is in contact with this
Good,
surface.
good. So as we discussed in the last class, whenever there is a surface of contact between two objects, you can consider a normal force to be acting. Okay. And because there is a string connected here, you can even consider tension to be acting, right? Now, Vanilla, you tell me, which way does weight act? In which direction does weight act?
Downwards.
Downward, correct. And what about normal force?
Upwards.
Why should normal force act upwards? Weight acts downwards because the earth is down, vertically downward, or center of the earth would be vertically downward from the object. So mg acts this way. Why should normal force act in the upward direction like this? Vanilla, in the name normal force, what does the word normal mean? Anyone? What does the word normal mean?
Perpendicular.
Perpendicular. Okay. So normal force, it's called normal force because it always acts perpendicular to the surface of contact. Here the surface of contact is inclined. So the normal force would be acting this way. Okay. So you don't call that as upwards. You should say perpendicular to the contact. I mean, surface of contact. this angle will be 90 degrees. That is why it is called normal force. Vanilla, is this clear?
Yes, sir.
Okay. And Rishi, can you tell the direction in which tension will be acting on this block?
This way, sir, like towards the right, like towards the right.
This way?
No, down, even more down. Like,
Okay, so along the incline you're saying, like this.
yeah, along the incline. Yes, sir.
What is exerting tension on the block this way?
Third, the string is exerting it from that side, so it should be opposite.
So why will it be down? Is the string pushing?
No, it's pulling.
Then how can it be this way?
Oh yeah, so the arrow will be towards that side.
Not at the arrow, it will be tension always acts towards the string. Okay, the string pulls objects towards itself. So there's a tension acting on the block this way. Fine. So these are the forces that act on it. It's a smooth surface, so we won't consider friction as of now. Under the influence of these three forces, the object is in equilibrium. Okay, it is given to you that the block is in equilibrium, right? Now we have to find out how much each force is. One force we know already, that is the weight of the object. W is equal to mg. We need to calculate the magnitudes of tension and normal force in terms of mg, theta and all. Try this, all of you. You just have to write net force is equal to 0. That means force in one direction or all forces in one direction, balance all forces in the opposite direction. You have to write equations accordingly. Think of how to do it. Any answers? Okay. See, whenever you need to calculate one of the unknown forces, to clearly visualize the situation, it will be better if you draw the free body diagram. And last class we discussed. Can one of you tell me what a free body diagram should show or what it should consist? What do we indicate in a free body diagram?
Sir, all of the forces acting on the body.
We must show the forces acting on the object. Okay, on the object, not the forces exerted by the object. Now in this case, we know these are the forces acting on it. And it will be better if you show all the forces with their tails common. So normal force, tension and weight. Okay, let's just extend this a little bit. These are the forces acting on it. Now we need to calculate the magnitudes of tension and normal. So as I said, we are going to make use of Fnet equal to 0. Now there's only one equation. There are two unknowns. Tension is unknown, normal force is unknown. So we'll have to use components of the forces. We'll have to write this equation in two independent directions. Fine. Now, one choice we have is to take x-axis horizontally and y-axis vertically. Okay. Call this x, call this y. Then take the x components and y components of the forces, balance x components, balance y components. You will get two equations, and there are two unknowns, so you can solve for them. Let's visualize the angle made by tension and normal. If you imagine a horizontal line here, if this angle is theta, then this angle made by tension will also be theta. Tension is parallel to the surface. Okay, the thread, the string is placed like that. It is placed parallel to the incline. We know normal force is perpendicular to the incline. So this complete angle between tension and normal is 90 degrees. One side the angle is theta, in between the angle is 90, then the remaining angle would be 90 minus theta, because the total angle has to be 180 degrees. Okay, is this clear to all of you, how we took the angles? If you have any doubts, you can ask. Fine. The surface makes an angle theta with the horizontal. So the wire also, or the string also makes the same angle theta with the horizontal. Normal force being perpendicular to the surface makes 90 minus theta with the horizontal. So let's indicate those angles here. Tension making theta, normal force making 90 degree minus theta. Okay. Pawan, tell me, what in this diagram, or out of all these forces, which forces or components are acting to the left? What did you say?
Tension.
Is tension acting completely to the left?
Not completely.
So there will be a component of tension acting to the left. Fine. Are there any forces or their components acting to the right?
Sir, normal component.
The component of normal, correct. So a component of tension acting towards left must have been balancing the component of normal acting to the right. There are no other forces acting left or right. Okay. So force in the negative x direction equals force in the positive x direction. If you write an equation that way, Pawan, continue. Tension magnitude is T, angle made is theta. How much is its component?
Sir, T cos theta.
T cos theta. Okay. How much is normal's component on the other side?
T sin theta.
N sin theta. Okay. It is n cos 90 minus theta, n sin theta. So we get one equation. T cos theta equal to n sin theta. Okay. This is one relation. We need to calculate both T and N. So we'll need two equations. One equation won't be sufficient. So force in the negative x direction, we equated to force in positive x direction. We got one equation this way. Next, Aishwarya, can you quickly tell me what all forces or their components act in the upward direction?
So the y component of tension and normal force.
Okay, how much will be the y component of tension? Anyone else? How much will be the y component of tension? The vector's magnitude. The vector's magnitude is t. With x-axis it makes theta. Then with y-axis it will be making 90 minus theta. So the magnitude becomes t sin theta. Next, the component of normal force in the y direction. Can one of you tell me that?
Sir, is it n cos theta?
It will be n cos theta, correct. Because with y direction, n makes an angle theta. With x-axis, it makes 90 minus theta. So with y-axis, it is theta. So n cos theta. Now t sin theta, n cos theta are acting upwards. The only force acting downwards is mg. Complete mg is downwards only, not just its component. So force in positive y direction equal to force in the negative y direction. That will give us the equation T sine theta plus n cos theta equal to mg. They are balancing mg. They are together balancing mg, not individually. So these are two equations. We can solve them and derive T and N. But if you try doing that, okay, it's going to be a little lengthy this way. We got T cos theta is equal to N sin theta. So we can say that T is equal to, just send cos theta that side, N into sin theta by cos theta, that becomes N into tan theta. Okay, put that in the second equation. So if you do that, it becomes N tan theta. In place of T, I'm taking N tan theta into sin theta plus N cos theta equal to mg. Okay, now tan is sin by cos multiplied with another sin becomes N sin square theta by cos theta. Okay, I'll do this quickly for all of you. You don't have to actually do all this. Equal to mg. Now take LCM. It becomes N sin square theta plus N cos square theta is equal to mg cos theta. I'm taking LCM and also sending the denominator to that side. And sin square plus cos square is 1. So left hand side becomes N into 1 equal to mg cos theta. But see, we had to write so many equations to get one force N equal to mg cos theta. Now with N we can find out T also, because we know T is equal to N tan theta. But this is a lengthier way to solve this question. A slightly simpler way to solve this question would be to take components or to take the reference axis, one along the incline. Okay, assume this is the x-axis. Now there's no rule that x should always be parallel to the base of your paper or the screen. You can take it whichever way you want. Call this as the x-axis and take this as the y-axis. How does this make things simpler? If you see now, normal force is completely in the y direction. Okay, tension is completely in the x direction. So you don't have to resolve them into components. You only have to resolve mg into components. Earlier, we had to resolve, like the previous way of solving, we had to take tensions components, normals components. So two forces had to be resolved into components and then balanced, which is lengthier. If you take them along the incline and perpendicular to the incline like this, which I have now suggested, you will only have to resolve mg into components. That is much simpler and you'll get easier equations to solve that way. Okay, so I want you all to solve it like this. Just a moment. So there's this inclined surface. Making an angle theta with the horizontal. The block was here. Let it be. You don't even have to show the block. We'll just treat it as a point. mg was acting vertically downward. mg always acts vertically downward. So I want you all to carefully think of how much this angle will be and write its components. Let us visualize the other direction also, the y direction. Normal force was acting this way. Tension was acting this way. Okay, so carefully find out how much these angles are and take the component of mg perpendicular to the surface like this and parallel to the surface like this. Write these components and then what you will do, you will equate this, you'll equate the force up the incline to the force down the incline. And after that, you will equate the force perpendicular outwards to the force perpendicular inwards. That's all. Once you take components of mg, the original mg should not be considered anymore, because you should either take the vector or its components. You can't take them both. Okay. So yeah, do this all of you. Resolve mg into components first. and then balance the forces. To get that angle, you can take help of this right angle triangle. The dotted black line is a horizontal line. mg is acting vertically, so this angle becomes 90 degrees. Do it quickly. Okay. Saket, did you calculate those components?
Yes, sir.
How much is the component along the incline?
Along the incline is mg sin theta, sir.
Correct. Because if the angle with the horizontal is theta, then this becomes 90 minus theta. Then component of mg that way would be mg cos 90 minus theta, that is mg sin theta, correct? And the component into the incline or perpendicular to the incline would be mg cos theta. Remember this, all of you. We will be coming across these situations quite frequently. If the angle of inclination with horizontal is theta, then weight component along the incline is mg sin theta, and perpendicular to the incline is mg cos theta. I think we had discussed this once, not as weight, but only gravity components we had discussed, I think, before, like in motion in a straight line sometime. Anyway, so what happens now is the block is in equilibrium. Now you don't have to consider mg anymore. Only consider its components. The block is in equilibrium. So normal force must be balancing mg cos theta. So you directly get n is equal to mg cos theta. You don't have to solve so many equations. You don't have to solve these many equations to say that n is equal to mg cos theta. Okay. And in the direction along the incline, tension balances mg sin theta. So you can directly say tension is equal to mg sin theta. Is this clear to all of you? So keep this in mind. Whenever an object is moving on an inclined surface, it will be easier to frame the equations if you take the axis, one along the incline and one perpendicular to the incline. Okay. If you use horizontal, vertical as a reference, then it becomes very difficult. I mean, it's going to be time taking. Fine. One of you quickly tell me, what is the net force on a massless object? Or how much can be the net force on a massless object? Okay. Tell me the mathematical form of Newton's second law. Equation.
F is equal to ma.
See, avoid saying F equal to ma. Make it a habit to say F net equal to ma. Okay, because if you just say F equal to ma, there is a chance that you will make mistakes. it's always the net force that determines the acceleration of the object, not one or few of the forces acting on it. You have to find out the combined effect of all forces acting on it. Okay, I'm telling this to all of you, not just to Rishi. Fine. So according to Newton's second law, or from what we observe in nature, Fnet is ma. Correct. If mass tends to 0, okay, then the right hand side will become 0, and if right hand side is 0, left hand side should also be 0. Fine. So if mass tends to 0, the force will also be tending to 0. You cannot have a net force. I mean, you cannot have a non-zero net force on a massless object. Okay. Force will be 0 and mass will be 0. What about acceleration? In this equation, if F is 0 and M is 0, what are the possible values of A? Like indirectly, I'm asking 0 is equal to 0 multiplied with what? This is F, this is M. What could A be?
Any value, sir.
Any value, correct. Okay. So net force on a massless object is always 0, but it can have any amount of acceleration as required. Okay. It depends on what it is connected to, what is dragging it or what is pushing it and all. Okay. Massless objects can accelerate without force also. That is the idea. Okay. As of now, we are considering strings to be massless. Okay. Or they are so light that their mass is negligible. If a string is so light that its mass is negligible, then net force on any part of the string should be 0. Okay. So in this case itself, you consider, or let's just consider a string from which or using which a block is suspended. Just a moment. Let's say using a string, you suspend a block from the roof. Assume block's mass is some 10 kg. So its weight would be 100 newtons. Okay, one of you quickly tell me, what is the other way of expressing its weight? In some other units, can you tell? We had one small discussion. When you ask a person their weight, they give you the answer in kg, not in newtons. So that way, how can you express the weight of this block? Okay, revise that later. We talked about something called kg weight. Okay, I got one answer in chat as kg per kg meter square. No, that is not how you express weight. We talked about something called kg weight. Kg weight literally translates to the weight of 1 kg. Okay, so I'm asking you what is the weight of a 10 kg block? It will be the weight of 10 kg. So you can say it is equal to 10 kg weight. Okay, 100 Newton and 10 kg weight are the same. Anyway, just look at the notes from 2 or 3 classes back. You'll understand. When we first talked about forces, we talked about that unit. Now let it be. This block's weight is 100 Newton and it is supported there by tension in the string. So tension in the string is 100 Newtons. Now the string touches the block at only one point, here. So here, the tension in the string will be 100 Newton. That's fine. The string on the other side is connected to the roof, the ceiling. One of you tell me, will the string be pulling the ceiling down or not? Will it be exerting a force on it in the downward direction or not?
Yes, sir.
Definitely. Okay. Like you tie something with a rope and you try to lift it up with a rope, you will feel pulled down by the rope. Okay. So the string will be pulling the roof in the downward direction. So it will exert some tension there also. But will that tension be equal to 100 Newton? greater or lesser? What do you think? On the block, it is definitely 100 Newton because the string is supporting the weight of the block. It is balancing the weight of the block. What about the force exerted by the string on the roof? Will that also be 100, more than 100 or less than 100? What do you think and why?
Sir, will it be the same?
Rishi, why do you think it should be the same?
Because the weight is 10 kg, and when it's being pulled on, it will apply like the same amount of force also at the string on the ceiling.
Okay. Okay. Yeah, that is one way of putting it. What you said is correct only. You can look at it this way. The block's mass is 10 kg. The string is very light. It doesn't have any mass. Okay. Now the roof has to support the string and the block. Fine. And what is the mass of the string and the block combined? It's still 10 kg itself. String does not have any mass. Okay. So the force that the roof must exert is also 100 newtons only, and it will exert on the string will exert on the roof. Okay. So it is 100 Newton, that is correct. Now you can look, you can think of the string as a collection of particles connected next to each other. Okay. You can take this as one particle of the string, this as the next particle of the string, and so on. But these are all massless objects. Okay, the string effectively doesn't have any mass. So these small parts of the string also won't have any significant mass. Now, if you consider any one particle, let's say that one which I've highlighted in yellow, on the lower side, it will be pulled this way. On the upper side, it will be pulled this way. There will be stretching. I mean, there will be a tendency to stretch everywhere in the string, okay, because of the weight of the block. So every particle of the string is like tending to get stretched, but the internal restoring forces will maintain its shape, will help it maintain the shape. Now on the lower side, let's say it is pulled by a force T. Because the particle is massless and the net force has to be 0, the upper side force also has to be T itself. So on every particle of the string, there will be tension acting both ways. Okay. So effectively how it works is somewhat like this. There's tension acting this way, there's tension acting this way. The particle below it will be pulling it. The particle above it also will be pulling it. They are all linked by bonds, chemical bonds. And they all pull each other like this. They hold each other like this. So basically, tension gets developed everywhere in the string, not just at the point where it is connected to the block or the roof. Every element of the string develops that tension. Okay, every particle of the string. And if the string is massless, the tension is going to be same everywhere. On particle, it will be this way. On roof, it will be downwards. Right? So if string is massless, in questions, they call it an ideal string. Okay, ideal strings are massless strings. If string is massless, then tension is same at all points of the string. But I'll have to put a star here because there are some conditions under which tension in a massless string also can vary from point to point. That happens if there are knots in the string. Okay, if there are additional connections made to the string, then tension in the same string can take different values at different points. Okay, for example, you imagine something like this. Let's say there is a rigid support and a person standing here. Assume they are holding a rope with one of their hands and pulling it towards themselves. When they are pulling it towards themselves, a tension develops in the string. Okay, but let's say some part of the same string is loose on the other side. Here the tension is high, where the string is held tightly, the tension is high. Here the tension is low, or maybe zero also. So in the same rope, because there is an extra connection in between, the person is holding the rope in between, tension on that side of the rope can be different from tension on this side of the rope. Okay. But if there is no such disturbance to the string anywhere in between, then it will have the same tension everywhere. Okay. Keep this point in mind. You need to know these ideas also in detail. In many books, they take it for granted that tension is same everywhere. Okay. But why is the tension same everywhere? The reason behind it is that the net force on a massless object is zero. So particles of the string are massless. So with whatever force they are pulled on one side, with the same force they'll be pulled on the other side, because the net force has to be zero. That way the same tension will be seen all along the rope. But if there are some additional forces in between from outside, then tension on one side of the rope can be different from tension on the other side of the rope. Okay. Now consider this situation. Suppose there's an inclined surface and there's a smooth pulley here. On this side of the surface, we kept one block. And on the other side of the surface also, there is a block, a different block. They are tied to each other with the help of a string, which passes over this smooth pulley. So the string can simply slide over that pulley without any resistance, without any friction. They are connected like this. Now, the blocks are not identical, they need not be identical. You have to find out. But tell me, is it possible to keep such a system in equilibrium by choosing the right amount of mass on either side? Can we keep this system stable or not? What do you think? Anyone? Can such a system be in equilibrium or not?
Yes, sir.
It's possible. Okay. So assume this angle is say 37 degrees and this angle is 53 degrees. And let's say the mass of one block, assume this side mass is 5 kg. You should find out how much mass should be placed on the other side such that the system is in equilibrium. System is in equilibrium means both the blocks must be in equilibrium. Okay. For that to happen, what is the mass of the block B? Surface is smooth. You think of what forces act on the blocks, balance them, calculate mass of the block B. Try this, all of you. I'll give you the steps also. First thing to do is to indicate forces acting on each block. Next thing to do, whichever force's magnitude you know, you write directly. As of now, the only force whose magnitude we can tell directly is weight. Okay. But in this problem, since they are on an inclined surface, you'll have to take the components of weight. So do that carefully. So take components of mg. And the last thing to do is balance forces and get m from the equations. Okay, do this quickly. Okay, listen all of you. The question is the problem is to calculate the mass of the block B. Generally, not just in this question, in any physics question, if you are asked to calculate something, name it first, like give it some name, okay, assign some variable to it. So now let's call the mass of block B as M. So our aim is to calculate M. Okay. So first step I asked you to do is indicate the forces. Yusuf, are you there? Okay. Pawan, quickly tell me the forces acting on A.
Sir, tension, normal force, and gravitational.
Tension, normal force, and weight, of course. Okay. Tension because there is a string connected, normal because there is a surface of contact, weight definitely because it has mass. Okay, good. We just discussed that if a surface makes an angle theta with the horizontal, then the component of weight along that surface is mg sine theta. Now in this question, the mass of the block A is 5 kg. So its weight mg is 50 newtons, but you have to take its components. 50 newtons component with this way will be 50 sine theta. And theta on this side is 53 degrees. 50 sine 53 is 50 into 4 by 5. 40 newtons is that component. Okay, I'm not writing the unit. 40 Newton is the component of weight of the 5 kg block along the incline. And it will also
Sir,
have...
1 second.
Yeah.
How is that mg sine theta? Isn't it supposed to be mg cos theta? Like the one.
Like in this problem you are saying, or...
No, sir, like the problem we're doing right now. Isn't it supposed to be mg cos theta?
Why do you think it should be mg cos theta? Let us look at it separately. Just a moment. Consider something like this. So the block is here. I made use of this angle, 53 degrees. So now this angle is theta, not the other one. Okay. Mg is going to be vertically downward this way. I want the component of mg along the incline. And the component of mg perpendicular to the incline. So let's visualize a horizontal line here. If this angle is theta, this angle is going to be theta. Then this will be 90 minus theta, which means this will be theta and this will be 90 minus theta. So the angle on this side is 90 minus theta. So this will be mg sine theta itself.
Oh, okay, sir. Understood.
Okay. Whatever happened on that side in the first question that we discussed today, the same is happening on the left side now.
Yes, sir. Yes,
Okay.
sir. Yes, sir.
So the left surface makes 53 degrees with the horizontal. The weight magnitude is 50 newtons. So 50 sine 53 becomes 40 newtons. 40 Newton acts in that direction. The other component of its weight, 50 cos 53. Cos 53 is 3 by 5. 50 into 3 by 5 is 30. 30 Newton, its weight will be pressing it against the surface this way. Okay. The other forces acting on it are normal force. Normal force acts perpendicular to the surface. It will be like this. And tension. It will be like this. Okay, these are the forces acting on it. And see, it is given to you in the problem that the system is in equilibrium. Okay. For equilibrium itself, you are asked to calculate the mass m. Now, for 5 kg to be in equilibrium, one of you quickly tell me, how much should the tension be?
Sir,
40. Tension has to balance 40. They are opposite to each other. So we have the magnitude of tension now, 40 newtons. But anyway, some of you may ask, why are we calculating tension? We had to calculate the mass on the other side. Let us get there now. If you look at the forces acting on the other block, its weight, we'll take it as mg for now because we don't know the mass. there'll be a component of its weight like this, mg sine 37 degrees, because the angle on this side is 37. Sine 37 is 3 by 5. So 3 mg by 5 acts that way. And the other component of mg cos 37, acts like this. That is 4 mg by 5. Let them be. And there will be a normal force acting this way, perpendicular to the surface. There will also be a tension acting this way. Now our aim is to calculate mass of the block. And the only way we can do it is by balancing the forces. Now see, the normal force on the left side and the normal force on the right side, normal force on the first block and normal force on the second block, they are not related to each other. Okay. So we don't know how much is N1 or N2. Had you known N2, you could have balanced it with 4 mg by 5 and you could have given an answer for M. But we don't know N2. Okay. The other thing we can do is try to balance tension and 3 mg by 5. Okay. But do we know tension? Yes. It's the same string that is connected to both the blocks. And there's no, the pulley is frictionless. So it doesn't exert any pulling force or pushing force on the string in between. Okay, the string is bent, that's fine. But the pulley doesn't pull or push the string. Okay, so it doesn't disturb the tension in the string. So we can say that the tension in the string will be same everywhere. So on the left side, that is why we calculated tension on the left side. We found the tension is 40 Newton. That means this tension is also 40 Newton. And now we can say that 40 Newton tension is balancing 3 mg by 5. Then m becomes 4 into 5 divided by 3. Okay, I cancel the zeros on both sides. 4 into 5 is 20, 20 by 3. That is the mass of the second block, which can keep the first block, which can keep the entire system in equilibrium. So you are asked to calculate the mass such that the blocks are in equilibrium. Equilibrium means net force is 0. From the force equation, you should get the mass. The only way you can do that is by balancing forces, including weight. Okay, and that's what we did in this problem. So go through this once again, all of you. If you have any questions, you can ask. Any doubts?
No, sir.
Okay. Fine. Let's discuss one case in which the system may not be in equilibrium. Consider a horizontal surface like this. Assume a block is placed on it. Let's say the mass of the block is some. Okay. Fine. Let's take it as 3 kg. Now, if the block's mass is 3 kg, we know that the weight of the block would be 3 into 10, 30 newtons. Okay. It is at rest. It is lying on that surface. Okay. It is simply staying there. No friction. And it's not stuck to the surface or anything. It's just placed there. Tell me, what minimum force is needed to lift the block? What minimum vertical force is needed to lift the block? Anyone?
More than 30 newtons, sir.
More than 30 newtons. Makes sense. See, weight of the block is 30 Newton and it will keep on acting like this. Tell me, in the absence of this force, what other forces act on this block? When it is just placed on that surface, what other forces act on it?
Normal.
Normal force will be acting. And when it is just placed there, you won't see the block going anywhere, right? That means the normal force is also 30 newtons. Okay, since it's staying there in equilibrium, these two forces must be balanced. There are no other forces acting on it. These two must be balanced. Okay. The forces on the block are already balanced. Now you just need to lift it up. Vanilla, why did you say we need 30 newtons to lift it up?
Because 30 newtons is acting downwards.
There is normal 30 newton acting upwards also, no? What will happen to that? Or why did you not consider that?
అంటే మనం దాన్ని ఎత్తిన తర్వాత నార్మల్ ఫోర్స్ యాక్ట్ అవ్వదు కదా.
Okay, correct. What she's saying is after we lift it off the floor, there won't be a normal force acting. See, normal force requires contact. Okay, when there is no contact, there is no normal force. But Vanilla, one more thing. You said after we lift it off the floor, there won't be a normal force. But I'm asking you, what is the force needed to lift it off the floor? ఎత్తడానికి ఎంత ఫోర్స్ కావాలి అనేది క్వశ్చన్ ఇక్కడ. ఎత్తిన తర్వాత ఎంత ఫోర్స్ ఎగ్జర్ట్ చేయాలనేది కాదు. Do you still, will you still say it is 30 or any other answer? Okay, fine. Listen, all of you. When there are no other forces acting, this is the situation. Basically, what normal force does in any situation, not just in this case, is, as I said, it has to prevent one surface from going into another surface. So it has to prevent one object from going into another object. For that, how much ever force is necessary, only that much will act. Now here, gravity 30 Newton is pulling the block downwards. So there must be a normal force of 30 Newton to prevent the block from going down into the table. That is why normal force is 30. In this same situation, on that 3 kg block, suppose you exert an extra force. Let's say you pull it up gently with a force of 5 Newton. Okay, so you all can imagine a situation like this. Assume there's a heavy object that you are holding on your palm. This book, it weighs almost 2 kg, which in newtons would be 20 newtons is the mass of this weight of this book. Sorry. Now my palm is supporting all that weight. So right now at this moment, the normal force exerted by my palm by my palm on the book is 20 Newton upwards. Weight 20 Newton is acting downwards. But if I somehow, like maybe I tie up this book with threads and start pulling it up, okay, or maybe like this, I hold it like this and start pulling it up with my other hand, then will the force on my first hand decrease or not? How hard the book is pressing onto my first hand, will it decrease when I start pulling it up gently or not? What do you say? If the book is tied to a rope or something and I start pulling the rope upwards, will it decrease the normal force on my other palm or not?
Yes, sir, it will decrease.
It will feel lighter. Okay. So suppose we apply a 5 Newton force this way, or let me show both cases parallelly. When there's no 5 Newton force or no additional force applied, the normal force is 30 newtons, because normal force is the only force which can prevent it from going down. Okay. Now, if there's an additional 5 Newton force acting upwards, what is the effective force which is pulling the block down, book or block, whatever it is?
25 Newton.
25 newtons. So how much normal force is now needed to prevent it from going down? In this case, the normal force will only be 25 newtons. It won't be 30 newtons. Okay. So normal force adjusts itself depending on the requirement. In the second case, okay, this is case 1 and this is case 2. In the second case, 30 Newton is weight, 5 Newton is an additional force that we have applied. The resultant of 30 and 5 is 25 in the downward direction. That is what makes the block press the surface. Okay. So normal force of 25 Newton is sufficient to prevent it from going down. So normal force will be 25 itself. So when the force F is 5 Newton, the normal force changes to 25 Newton. Will the block lose contact? Or will it still be in contact? When you pull it up with only 5 Newton force, will the block lose contact or stay there itself?
It'll stay there only, sir.
Okay. Others also, are you all convinced or not? If you have any doubts, you can ask. Okay, it will stay there itself. You have not applied sufficient force to lift it off the ground, okay, off the table. So it will stay there itself, but the normal force will be lesser. Now you increase this force. Maybe change that force to 20 newtons. Aishwarya, tell me, how much will be the normal force now?
So 10 Newton.
Now it will decrease itself further. It will only be 10 newtons. So as you increase that force, that additional force that you are applying in the upward direction, as you increase that, the normal force decreases itself automatically. Okay. And when you apply sufficient force in the upward direction, the normal force completely disappears. That is when the block loses contact. Fine. Now you all tell me, how much force is needed to make normal force 0?
30.
30 newtons. If the applied force is 30 newtons, the normal force becomes 0. That means the block is not pressing the surface anymore. Means it is ready to rise up. Okay. Now, when I first asked the question, Vanilla said we need a force more than 30 Newton. Okay. What she said is correct. 30 Newton is its weight. You need a force more than the weight to make it go up, because we need a net force in the upward direction. But can any of you tell me a number? Tell me the number which is next to 30.
31.
No. Can't you think of any numbers between 30 and 31?
30.1.
Can't you think of any numbers between 30 and 30.1?
30.00.
Okay. So I'll repeat my question. Can you tell the number which is immediately after 30? Anyone? We cannot. Pawan, what did you say?
We can't say, sir.
We can't. Okay. So when they ask you a question like this, what is the minimum force required to lift the block? You know it is more than 30, but you can't specify the number more than 30. So you will write the answer as 30 itself. Okay. So minimum force required to lift the block is 30 newtons. Okay. Even when you know that it's anything greater than 30, you will say it is 30. Mathematically, it is valid. Okay. And options also will be like that only. Now I can ask you the same question in reverse. What is the maximum upward force you can apply such that the block does not lose contact with the ground? Okay. Now we have seen this. If the force increases, the normal force decreases. Like when the force is only 5 Newton, normal force was 25 Newton, and there is still contact. Okay. As the force is increasing, the normal force is decreasing, and the block is getting a tendency to rise up. Now my question is, what is the maximum force you can apply in the vertical direction such that this block does not rise up? What will your answer be?
30.
30 itself. Okay, because 30 will balance, it won't rise. Okay. So if you are asked a question that way, maximum force such that the block, this is the symbol for such that, you are supposed to know this. Okay, maximum force such that the block does not lose contact with the surface. The answer to that question is also 30. Okay, minimum force required to lift it is 30. Maximum force to not lift the block is also 30 itself. Okay, and options also will be given that way. You don't have to bother much about just greater than, just less than, and all. Okay, so there are a few things which we learned in this problem, that normal force should be calculated based on the situation. There's no direct formula for it. You have to look at the other forces acting on the object in order to tell how much normal force acts on it. Okay, the only thing we know for sure about normal force is it tries to prevent one object from going into another object. For that, how much ever effort is necessary, that much effort it will put. Okay, so in first case 30 Newton was necessary, 30 Newton will act. Second case 25 is sufficient, 25 only will act. Okay. Next question. Okay, similar situation, there's a block. Assume its mass is some 7 kg. See, I have this habit of drawing objects without touching each other, but this block is on the table, they're in contact. Doesn't look like they are in contact, but you assume they are in contact. Because adjusting all that will take time. So situation is like this, the block is at rest. The block is initially at rest in equilibrium. We had discussed this point also in the last class, or maybe before that. Objects can be moving in equilibrium also, but this object is in rest and in equilibrium. First question, calculate the normal force on the block. Second question, if an upward force of how much shall we take? Just a moment. 105 newtons is applied on the block. Calculate its acceleration. Okay, solve this quickly, all of you. Okay. Any answer? Initially, how much is the normal force on the block?
70.
70 Newton, correct. Because its weight, 70 Newton will be pulling it down. Normal force has to balance that. Okay. Next, if we apply an upward force of 105 Newtons on the block, how much will its acceleration be? I got one answer as 3 meter per second square. We'll discuss. But I don't think 3 is correct. Okay, Pawan, your answer is correct only. Okay, listen all of you. When we start applying a force of 105 Newton on it in the upward direction, will normal force still act on the block? Will normal force still act on the block when we apply an upward force of 105 Newtons?
No, sir.
Why not?
Because the block will rise up, there will be no
Huh.
contact between the block.
See, as
and
I said, correct. As I said, normal depends on the other forces acting on it. If you want to check whether normal force acts or not, or how much normal force acts, you see the other forces first. There's 105 upward and 70 downwards. Upward force will dominate. This block naturally has a tendency to rise up. Not naturally. Under the influence of these forces, it has a tendency to rise up. It doesn't have a tendency to press down on the floor. Then why will normal force act? It won't act. Okay. So while answering the second part of the problem, you should not consider normal because it won't act, right? So there are only two forces acting on this block now, 105 upwards, 70 downwards. You know the forces acting on it, you know its mass, and you need its acceleration. Based on force and mass, how can acceleration be calculated? Can one of you tell? From force and mass, how can we calculate acceleration?
Fnet by mass, sir.
Right, Fnet equal to ma. Okay. As I said, the use of this term net is very important. So you get acceleration as net force divided by the mass. Okay. There are two forces, 105 upward and 70 downward. Then what is the net force? And in which direction is it? How much is the net force and in which direction is it? Aishwarya, can you tell the net force acting on this block?
So 35 Newton upwards.
Correct. So 105 upwards and 70 downwards. Since they are exactly opposite, you can directly subtract them. Okay. So the net force on this block is 35 newtons in the upward direction. And if net force is 35 newtons and mass is 7 kg, the acceleration will be 5 meters per second square upward. So it will rise up with that acceleration. Okay, if any of you has any doubts, you can ask. Okay, we'll close this session here. We'll just go through what all we discussed today. So first was a case of equilibrium where we calculated tension. The block was placed on an incline. Okay, and next we discussed why the tension in a massless rope will be same everywhere. Okay, and when it may not be same, even if the rope is massless, tension may not be same everywhere in some cases. Okay, for now we'll not take such cases. We'll learn about them a little later. Then we'd solve this problem of equilibrium, where you are asked to find out the mass when the system is in equilibrium, or mass that keeps the system in equilibrium. And we discussed how normal adjusts itself, and one case where normal disappears and the block accelerates. Fine. So today is what? Friday. Can you all attend class tomorrow?
Yes, sir.
Saket, what about you?
Yes, sir.
Sir, I may not be able to attend, sir. If it's a bit
Okay.
earlier, I will,
Early means what time can you attend?
sir, like around 5:30 or 6.
So 6 to 7, 7:30 you can attend.
Yes, sir, no problem.
Uh, is that okay for others? Can I take class tomorrow at 6 o'clock?
Yes, sir.
Okay. Yusuf is saying he won't be able to attend. Otherwise, what about Sunday? I'll give you some options for Sunday.
Sir, Sunday what time? Because I
That-
have exam from
from
5 to 8, sir.
evening 5 to 8 you have exam. Okay. So afternoon 3 o'clock, can you all attend class on Sunday? 3 to maybe 4:30. We don't have to record all this.